The plan is molecular geometry and then geometry and polarity and how they relate. So whether it's polar or non-polar based on its structure. I don't know. So that's not awful, either one of them. So the goal is be able to draw molecules given their formula, like their molecular shapes. And like we should be able to name them and describe them and all that too. And then be able to determine the polarity of a molecule given its structure. You're not going to catch that in your mouth. The odds are very low. I'm just a dream killer, but it was a big square. Okay, well, you have a bigger mouth. Okay, I think we all know that. Just kidding. I know, actually, that's very true. Okay, here we go.
I was at the dentist this morning and I made a realization. I'm only quiet when I'm at the dentist, and that's like only when they have the tools in my mouth.
Yeah, when your drool's about to suffocate you, you're like, I hate the dentist so bad. I went to the dentist like 6 months ago and he's like, bro, you got a lot of cavities. And I was like, no, I don't. And I never went back. So we'll see. No. Yeah. There you go. That's like the motto of 2020 and 2021 right there. But I'm not going to go any farther. Okay. What I would do today is like make a table. It's a lot like what we already did, but it's actually a second version of it. So here we go. We ended yesterday right here, I believe. And that was within each electron domain, there might be more than one molecular geometry. Timeout. Will you tell your partner what an electron domain is?
I think I can do it. I choked. I don't eat drinks. I have to use it. But yeah, that's why you don't throw grapes at it.
Okay, here we go. An electron domain is where electrons reside around an atom, right? You okay with that? Okay. Tell your partner how many electron domains that has. How many electron domains does B have?
3.
3 is the correct answer. Everyone okay with that? You got it. All right. Okay, next. How many electron domains does this one have? 4. So, all right. What would the electron domain geometry be here? Trigonal planar, right? Or of C. We wouldn't find it unless it was with something else. So Blaine asked, what would it be of C or carbon, if you want to call it that? We don't find the geometries unless it's a central atom. So like if I put O and a double bond there, then we would find that. Okay. All right. So for B, the electron domain is trigonal planar. What would the molecular geometry be? That's a P right there. Trigonal planar as well. It's the same. Why would it be the same? All right, because every domain is a bonding domain. Good. All right, what would A have been? All right, that would have been, no, tetrahedral, right? Tetrahedral. All right, because Seth is smart and he has his paper. All right, that would be the electron domain. What about the molecular geometry? Same. Tell your partner why it's the same. All right, because everything that A is bonded to, or sorry, all the electrons with A is bonded to something else. All right, I wasn't going to do C, but we might as well while we're here. We have element C or carbon. All right, what would its electron domain be? It has three, so trigonal, planar, right? How about its molecular geometry? No, you guys have said it. It's bent. Now listen, it's not as bent as water, but it's still bent.
So why?
It's because water had two, so it squeezes them closer. We'll go over that actually in like 3 slides. But all right, so this one is different because of non-bonding pairs. Pretend that one was not there. Okay, easy enough, sort of. Okay, so yes.
Do they only like break if they have like the other pairs off the top?
What do you mean by break?
Or like bend, that's like that.
Oh, they bend when there's non-bonding pairs. Yes. Speak.
So if there's non-bonding pairs, it can be linear or bent or just bent.
It can be linear or bent. It just depends on what you're looking at.
And if it's bonded, then it's usually what the electron is as well.
Yes, if it's all bonded pairs, then they match. They're the same.
But it's not bent.
No, we're going to go a lot farther. That's why we're going to draw this table coming up. Okay, so here we go. Linear. So if I was drawing a table, I would just draw it like this.
Write the word.
In this domain, there is only one molecular geometry, and it's called linear. So note, if there are only 2 atoms in the molecule will be linear no matter what direction the domain is as well. So if you just have A, B, and I don't care if A and B is here, like, or A and B is here, it's still a straight line between the two. You all right with that? Okay. All right. So when things are linear, there's no non-bonding domains around the central atom. Yes, there is here, but not around the central atom. So linear is a piece of cake. Linear will make linear. So far, okay? Okay. Now, we have 3 electron domains. We now have trigonal planar. All right. The bonding domains would be 3. Like these will match on the top rows, but then they change. Okay. If you have 3 and none of them are non-bonding, then it stays. So the lesson today is the molecular geometry and electron domain geometry are always the same if they are all bonding or there's no non-bonding. Okay, now this is what we just did a second ago, right? If we have trigonal planar, but 2 are bonding and 1 is non-bonding, we end up with a structure that is bent. And when we draw the molecular geometry, this piece wouldn't be there. It would just look like B, A, and B. Now, if I was drawing water, it's different. So the H's and the O's, it would just be a sharper angle. But we'll get to that one later because water doesn't belong here. Tell someone that sits close to you why water wouldn't belong on this slide. Because water has, I'm looking for the number 4, it has 4 electron domains. So it would be completely somewhere else, right? Okay, so this is what you need to know, and it is a lot. I'm aware of that. You need to know how to determine this, and you need to know that it would be that name, and you need to know, hey, if it's 2 to 1, then the structure's bent. Like you just have to know that. That's a required part of AP chemistry. So far, okay? Okay, now, there's going to be 2 or 3 slides that seem like we've moved on. We're going to come back to 4, 5, and 6 after these couple slides. Okay. So this next little piece is talking about how the non-bonding pairs affect the bond angle. So non-bonding pairs are physically larger than bonding pairs because they are not attracted to multiple nuclei. So what that means is if there's electrons here, they're positively pulled towards here, right? If there's electrons here, they're pulled that way and that way. So if they're bonded, where they are is smaller. If they're not, it's larger. So it would be like we're blowing up balloons that if they are non-bonding pairs, they're a bigger size than the bonding ones. So they will push those away. Okay. So therefore, their repulsions are greater. This tends to decrease bond angles in a molecule. So all of these here are tetrahedral, which means all of them have 4 electron domains. We would expect their angles to be all the same, but they are not. In methane, all of them are bonding, so they push equally, and it's 109.5. This is a number you should memorize. The other ones you don't have to memorize. You just need to know they're less than that. In ammonium, we have a non-bonding pair that squeezes the H's closer than this bonding pair would have in methane. So that squeezes them just 2 degrees closer to each other. Not a huge deal, but it is still a deal. All right, and then water, there's 2 non-bonding pairs, which force them even a little tiny bit closer to each other, 104.5. Okay, now I'm going to say it one more time on this part, what you need to memorize. You need to know tetrahedral is 109.5. Like that's something that's part of the standards. And you need to know that if there's non-bonding pairs, this would be smaller, the angle, and this would be smallest. But you don't have to have their numbers memorized. It would still be a 104.5 here. They're all the same. Okay. No, you don't like that? It squeezes everything.
Well, yeah, but like, because does it just mean that like, where are you measuring the angles from?
Wherever I feel like.
Like, where does those, okay, that makes sense.
Like between here, between here, between here, and then like the back one between there. Because no matter if I have all 4 of those, if I rotate them around, well, which one's the one going up and down? It doesn't matter. They're going to be the same. Okay.
Well, like when you decrease the size of the angles, that like mess it up because like you can't say that we have like 360 degrees. You like say that the angles are instead of 60 degrees, there would be 50 degrees. Well, we can't just have 350-degree angles that makes it a complete circle. That's not how math works.
I guess you're right. So I don't know how math works, I guess. Okay.
Doesn't by increasing one of the angles or decreasing it
I guess. That's a good question. All you gotta know is they're smaller. How about that? I had salsa for lunch. I feel like I have stuff in my teeth.
You don't, you're good.
Okay, good. Because one of the teachers at lunch had green in his teeth, and I just didn't tell him. I have white in my teeth. That's rare. They're usually yellow. All right, good points. I don't know. It'd be, I guess by your logic, it has to be different, but I'm not going to worry about it. Okay, here we go. All right, double, I guess this proves what you're saying right here. Double and triple bonds do the same thing. They place greater electron density on one side of the central atom than do single bonds. Therefore, they also affect bond angles. Okay, You do not have to have these memorized, but you would need to know in a double bond, this angle here would be bigger than normal. And this angle here would be smaller than normal. So the angle where the doubles are bigger. And the angle where it's not is where it's smaller. Now, you don't have to know what they are. You don't even have to draw them, right? It would just be like a conceptual question. It would say between if I know how AP works, they would say this is A, B, C, and D, and they'd ask between what was the largest angle, and you'd say A to C or A, B, D or whatever. Like they'll only ask it in a multiple choice way. Okay, now what does that have to do with what we're talking about? We'll wrap it all up. Well, it kind of does. Okay, back to our chart. You ready? So now we have 4 electron domains. If they are all bonding, then tetrahedral electron domain geometry and tetrahedral molecular geometry. If there's no non-bonding, the ED and the MG are always the same. Okay, if it's now 3 to 1, we have a pair here pushing these down, right? So we now have a 1 thing in the middle and 3 around it. We would think, oh, that's trigonal, but no, they're being pushed down, so it becomes trigonal pyramidal. And ammonia is the most normal example of that. Okay, then if I have 2 that are bonding and 2 that are non-bonding, I end up with bent. Okay, the names, sometimes like you can memorize them, sometimes they just make sense. Oh, come on. So Tetris is a game you play with everything that's made out of 4 blocks, right? Tetra means 4. So tetrahedral, 4 things come out. Trigonal, that probably means 3, which is right. Pyramidal means that they're not on the same plane. And that's because they're being pushed away.
It's like a little triangle
Pyramid. Yep. Like kind of weird, but yes. All right, and then we have bent, which kind of makes sense. We would expect it to be a line, 1, 2, 3 things, but it's a line that's bent. Bent. Okay, so far okay? All right, now when we get to 5, there's some crazy names, and 6 as well. But we'll be okay. Okay, now we talked a little bit about this before yesterday. When we get to trigonal bipyramidal electron domains, there's 2 distinct positions in this geometry: axial and equatorial. That sound familiar? We talked about it yesterday. This will matter because we're going to talk about the shapes in a minute, and we need to know which way they're going to go. So axial is the ones that go through vertical, just like the axis of the planet does. And equatorial are the things that go around. So we might use that verbiage here on the next slide. Fair enough? Okay. Okay. I thought we were the chart. Yeah, it's the next one. So here we go. When we have this trigonal bipyramidal, we have an option of putting it on an axial or an equatorial, right? And it's all about the bonds. Lower energy conformations result from having non-bonding electron pairs in equatorial rather than axial positions in this geometry. Now, what does that even mean? It means if you have a non-bonding pair, you're going to put it on the side instead of up here. Okay, that's because of the interactions. There's like 120 degrees between all of these, right? If you put it up here, there's 90 between each one. And it's not as happy messing with the 90. It would rather mess with the 120. You okay with that? Okay, so here we go. Trigonal bipyramidal has some interesting things. If it's 5 and 0, it's trigonal bipyramidal, and that's PCl5. All right, if it's 4 and 1, we end up with what we call seesaw. And seesaw is kind of weird. I wish they would just draw it sideways so it kind of made sense. But seesaw is like 2 legs of your seesaw and then the other part that you would sit on. You with me? If you rotate this thing like sideways, you can sort of see how it is a seesaw. And if you can't, I apologize that my drawing skills didn't make it perfect knowledge for you. If we have 3 to 2, this is my favorite one. It's called T-shaped because my name's Tom. All right, and you can see the T, and it's sideways in this picture. Okay, apparently I'm holding this crooked. It's sideways, but there's your T. Okay, T-shaped. Then, who would have ever thought we could get linear when you had 5 things involved? If we have 2 bonding domains and 3 that are non-bonding, the 3 go around here and they offset each one the exact same. So it just stays in a straight line. It's linear. Good. Your face, you didn't seem like you liked that at first. All right. You ready? I'll just have some flat, warm Mountain Dew. I couldn't even see it. Here we go. I got this. Ready?
It was like not even a foot off.
I can't do that trick in boots. Okay. Whoa. There's other empty Mountain Dew bottles in there. Where did they come from? Empty water bottle in here. I really do wonder where that one came from. All right. Can you see past my head, Brown? Okay. So that's 5. We have 1 left. It's a 6, which we call an octahedral, because that makes total sense, right? Because 8 sides.
8 sides.
Okay, you're fired. You'll actually like this one. Yes, sir. Yeah, it's shorter. Bonding domain 6 to nothing, octahedral, octahedral. 5 to 1 is bizarro. All right. Now, in an octahedral, you may remember from the other chart we made, every angle is a 90-degree angle, right? So do we have axial and equatorial? No, because no matter where I spin it, it's still a 90-degree angle. So this might look like I put it on an axial, but if you spin it, it goes wherever it wants. So there's just 3. Okay, so I have 5 to 1. I end up with what's called square pyramidal. And that's because it makes a square. It's hard to draw a square. I don't know what that line was doing. And then if you connect them all, it's like a real square pyramid. I read a dad joke yesterday, but it wasn't a dad joke. It was a history joke. It said, why are the, what was it, crap? Why are the pyramids in Egypt? I think it said. Anyone know this? This is a roast of England. It's because they're too heavy to transport to a British museum. Because they stole pretty much every antiquity ever back in the whatever ages. The Crusades, that's the word I'm looking for. Okay, sorry. There's your history nerd joke for the day. Okay, thank you. I'm glad. Square, pyramidal. All right. And then if it's 4 and 2, it's just a square. That square, I don't know. It's hard to draw them. Do better, Tom. You've got this line tool here. That means it's a square and there's not another one on top or the bottom to make it bend. Yes, Seth.
So with 5, the unbounded will be on the side, but on 6 it will be on the
On 6, it'll be anywhere because they're all the same. These are drawn top and bottom, but really they're anywhere. It just rotates it. That one's called square planar. Sorry. Okay, attitude. That's it. That's it.
Why aren't there any more?
It's a good question. I don't remember. There's a reason.
Oh, is it because like it can't hold on to the electrons if it's got any less atoms?
Maybe. I was afraid someone's going to ask because I was like, oh yeah, this stops and I don't remember why. It's like 2 sentences in a book. Fine, I'll find it, but not right now. Okay, are we ready? Here you go. This is a question you'll see again. It says molecules that have planar configurations include which of the following? Configurations is another way of saying their shape, like their molecular geometries. Planar, oops, I'm in the line tool. Now, there's a good way to do this. We'll draw them out and then I'll tell you how to do it fast. Are you ready?
Yeah.
So BCl3. Ooh, I have boron with some 3 really electronegative things. Okay, so this is that weird one. B, Cl, Cl, Cl. Do I have any electrons in the center? No. This is one of the exceptions, remember? Boron, try anything, really? Not anything, but I hear some mumbling by the door. It's driving me a little crazy. No, it's you guys. Okay. What would the name of this be? Oh, I forgot I had chocolate in there getting melted. What would the name of this be? Shh. Not the name of this, the structure. Trigonal planar, right? So would this one have planar shape? Yes, it does. CHCl4, or sorry, 3. So our central atom is C, right? What would you call this if it has 4 electron domains? Tell your partner. Tetrahedral. Is a tetrahedral all on the same plane?
No.
No. So would this one? No. All right. NCl3. Now, is this going to be the same as this one? No. Do you know why? Because chlorine can't boss nitrogen around as easily as it can boron. They're too close in their electronegativity. So they're going to have to, we have to octet the middle one this time. What's that? Well, we'll see. We'll see. Honestly, it's easy. We have 5 plus 21, right? Does everyone know where I got 5 plus 21? Benson's? Okay. Not picking on them. They were gone. All right. So I have 26. Well, we've said a few times 26 is a great number. What does that do? It octets everything if there's 4 of them. So that's great. So I have a Cl, I have a Cl, I have a Cl, and I have a non-bonding pair, right? Or how many electron domains do I have? 4, and I would call this? No. Tetra. Boom, home run. We got that one. 4 means tetrahedral. Does that end with the word planar? Nope. So which one? Only this one, right? Only the first one had planar configurations. Good. Okay. The Lewis dot structure for which of the following molecules shows only 1 unshared pairs of valence electrons? Why? When you have a diatomic molecule, we have Cl, Cl, and then dots everywhere, right? If you have N2, it's a triple bond, but you still have to octet. So there's 2 that are unshared. You okay with that? Okay, so A and B are gone. Why don't you try these and see what you get? Oh, I'm waiting. Oh man, what did I do? Oh, I forgot about that. How could I have forgotten about that beautiful artwork? Is that bad that my mouse is doing that? Any computer nerds out there? It doesn't mean the world's going to explode any second. This is for normal chem, not you. Unless you want to test tomorrow. Okay. How we doing? Anyone have an answer? Okay, anyone completely lost?
I don't think I'm complete.
Seth, the box, worst decision of your life.
I don't think he was decided to. I think he was kind of cool.
He was voted in by his peers. And Seth is that dedicated to all of you. Yeah, doesn't work if you're in Hawaii, probably. California.
Hawaii? That one.
Okay, I'm not going farther. It's this one. It's this one. Oh, man.
You started at the bottom?
CCl4 looks like that, right? They're all bonding. H2O2, HOOH, right? Double bond, single bond, it's not a triple bond, so it doesn't matter, right? There will be non-bonding pairs involved here. I think it looks like that if I remember. It doesn't matter, I don't even remember. But once you find your non-bonding pair, then there's your answer. Thanks, Goddard. What, Seth?
So on the H2O2, those also have unchecked pairs. Or it doesn't because it also be two bonds.
Only has one.
Oh,
And I don't know that I did this right. I have 2 plus 12 is 14.
yeah, you have two little.
1, 2, 4, 6, 8, 10, 12. All right, so I didn't need a double bond, right? Okay, I didn't know, I just made it up, but I knew for sure no matter what I had more. Okay, here we go. This is on your test. These will be in different locations, but you'll have to do this. There you go. You have a word bank. In AP, we do not talk about a pentagonal bipyramidal. That would have been this one. So ignore that. Another Tim above us. Okay, ready? Go. Fill that out as fast as you can. I'm done. What? You can use one more than once.
Oh, yeah,
Okay, I'm going to give you one more minute.
Octahedral, 6 because there's 8.
All right, are we ready? Whether you are or not, we're moving on. Okay, ready, team? You can use them more than once. So what is this? Linear. It's a straight line, right? All right, what's this one? It's kind of weird. That's a seesaw because you got your seesaw you'd sit on here, and then there's the balancing, the fulcrum. What would this one be? Linear. How about over here? Square pyramidal. You okay with that? What about this one? Linear. No matter what angle you look at this, it would be a line because there's only 2 total atoms. Questions? No, never mind. All right. How about BF3? Trigonal planar. How about this one? Bent. That's the baby bent, right? Versus the big bent, which is coming. I don't. Is that Chris?
Oh, you're exactly.
Probably Chris. All right, what do we have here? 1, 2, 3, 4. Tetra. This one's kicking your butts. How about this one? Square.
Oh, that's.
It should have been. This is the one that's bent more than that one was bent. And you don't have to know that really, but whatever. Okay, what is this one? Octahedral. How about this one? Okay, what do we have here? Trigonal pyramidal. And then this one? T-shaped. How many can do it? You can do it, right? Aisley? Sorry. These come from you. This starts with Lewis's. Okay. Oh, sorry, what?
My hand was in the air. Did you see that it was in the air? Yes.
I'm sorry I didn't validate you at first. Okay, on the test, you'll get a piece of paper that is just that and the words. I'm pointing over to Davis. And you can do okay. All right. Okay. Whoa, what if we have big molecules? Then chill. No, it's easy. Okay, so here we go. I just did it. We did this at the very start of class, and it wasn't bad. You just talk about each individual central atom at a time. So you wouldn't just be like, oh man, I don't know. So I'm going to start right here, and I'm going to look at O. How many electron domains? 4. 2 non-bonding. So this would be bent because it's 4 and 2. It's tetrahedral, but 2 are non-bonding, right? All right, then I move my rectangle and I look at this carbon. How many electron domains? 3. All right, how many are non-bonding? 0. So what do I call this? All right, trigonal planar. You okay with that? Then I move my rectangle. The only other central atom left is this carbon, correct? All right, so what would it be? It's, yeah, it's good. It's 4, it's 0, so it's tetra. That's all you do. Look at them individually.
So when like the thing is bent, the OH at the end of it, when it's bent, does it bend away or towards the other molecules? So like, what
It would bend as the next closest thing would be this O, so it would bend this way.
Correct.
So that this H and that O aren't close to each other. Okay, so we can draw this whole thing if we needed to. I don't really want to, but we'll do it anyway. So we'd have this, 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 and then this would come off, right? And then we'd have that like in a trigonal. You with me? And then this would be bent this way. It would look like that. This would be the C. This would be the other C. This would be the O. So we have our tetra, our trigonal planar and are bent.
Wait, would you not need the, so, because you have the O there, and there's two things coming out of it. You have three.
Oh, that was another C, wasn't it? Sorry.
Yeah.
It was two C's. I just wrote a O.
Well, no, like, so on the actual.
Oh, here?
But there should only be one.
Nuh-uh.
Oh, you're right. You're right. You're right. Hold on. Hold on. There we go. Sorry. Yeah, you're right. Remember when I said I didn't really want to? It's because they're easy to screw up when you draw the bubbles. All right. So larger molecules, I'm not spending any more time. Just analyze each one by itself. Okay. Well, here's the better picture. And mine was a little bit like trailing off, but it was pretty close.
I also think you're a great singer, so.
Thank you. You're super wrong. The bubbles? Yeah, the space filling models. All right. Now, we'll come back to that, but I gotta go through this to feel like I finished what I wanted in a day for once. I got plenty of time. Because if we know what we just did, then this is easy. In chapter 8, we discussed bond dipoles. That was when things were polar or not. They were the arrows with the plus sign. You with me? Okay. But just because a molecule possesses polar bonds does not mean the molecule will be polar. Now that's really messed up. But we know a new language called the structure. So we know carbon dioxide is linear, correct? We know oxygen is much more electronegative than carbon. So this oxygen pulls the electron this way. But what does this oxygen do? Pulls it exactly the opposite way. So where's the net movement? There is not one. So even though carbon and oxygen is a polar bond, carbon dioxide is not because it is linear. Interesting. All right. So if it's bent, it's going to be polar. So water, water is an O, and its structure, because these non-bonding pairs, I don't like how far that angle is. I shouldn't care. It doesn't really. Oh, I did the same thing. Okay, we'll just bring it down here. Now, here we go. The dipole moves that way and that way, right? Has anyone ever had physics? Wow. You haven't? Okay. In physics, we have what are called vectors, and we add them. And let me see if I did this right. Nope, they're connected. Hold on. Okay. They have a movement. So look, I'm going to take this vector. I take one of them, look, and I take the tail of one and put it on the head of the other. And then I draw what's called the resultant vector, which means the overall movement of the electron would have been this way. So since the electrons are moving that way and that way, I do have a dipole. And so this would be polar. But if this was trigonal planar, we had a pull like that way, and that way, they cancel each other out. So this would be non-polar. Okay, stick with me. So by adding individual bond dipoles, one can determine the overall dipole moment of the molecule. So once again, if we would have added these arrows on top of each other right here, where does it go? It goes nowhere. It is the same place it started. So that, and you don't have to draw these out like this. You just have to know, hey, if it's linear, all right, and it's not just two atoms, if it's linear, it's going to be nonpolar because the poles offset. If it's bent, it's going to be polar. Okay, so here's the summary. You probably won't have time to write it, so this is picture time. Molecules for which their central atom is symmetrically surrounded by identical atoms are nonpolar.
This is no fair. Turn around.
Okay, so CCl4 should definitely be something that's polar. But since the chlorines are symmetrically surrounding the chlorines, all the dipoles cancel out. Okay, next, all major shapes, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral will produce nonpolar molecules as long as all surrounding atoms are identical. There's a key thing here. All of these have zero non-bonding. This is what makes it easier. If you have no non-bonding, it's going to be nonpolar in these major shapes. If you have non-bonding, it's going to be polar. The presence of lone electron pairs on the central atom will usually, that's most of the time good enough, mean that the molecule is polar. Some exceptions include linear and square planar molecules that we'll talk about tomorrow. Okay. I wanted to get to this slide. Take a picture and see if you can figure that out. So we already did the chart. It's the same chart, but now I'm asking, are they polar or non-polar? So just your gut feeling, is this one polar or non-polar? Non-polar. Your feeling right here. Polar. Okay, keep on going. You guys are amazing. Thank you so much. We'll see you.